Now the question become, how do we choose the group for reduction? Okay. For this, let's understand couple of definition. Okay, like implicant, primary implicant, essential primary implicant. So an implicant is any product term of a SOP form of expression. Any product term you can think that's an implicant. A prime implicant is a product term which cannot be covered by any other more general terms, or the reduced term with the fewer literals. Okay, fewer literals. So think like by combining these neighboring ones, what you are essentially doing is combining them and reducing into fewer literals, in a term with a fewer literals. Okay, so by consuming more and more and more, making the group bigger, you are practically making a reduced form of the term, reduced form of the term. So a prime implicant is a reduced form which cannot be reduced further in that given Boolean expression. That's the prime implicant. Now, an essential prime implicant is a prime implicant that covers an output of the function in such a way that no other combination of prime implicant can cover. Okay, let's take an example and we'll see that. I will try to understand that concept. So this example, for variable w, x, y, z, which is sum of min terms 1, 3, 4, 5, 6, 7, 12, 14, which essentially will become like this w bar z and x z bar, but I'm just trying to show you in the example. Let's say we can group of maximal 1, 3, 5, 7, and we can group 4, 12, 6, 14. Okay, and let's make a group another, like it's a possible group 4, 5, 7, 6. With that, what happens, this green group, we are saying that this is the essential prime implicant. Okay, so one thing you need to know, both these green groups and red groups, they are all prime implicant. Okay, prime implicant, because by definition this is also a group which reduces a term to a point where it cannot be further reduced. Okay, so all this group 1, 3, 5, 7, 4, 5, 7, 6, and 4, 12, 6, 4, 14 are all prime implicants. Now these two are essential prime implicant. If you look at this big, like these two groups, it contains such member which are not included in any other group. For example, for this group of 1, 3, 5, 7, this 1 and 3, this is not covered by any other group, right? And also, if you look at this group of 4, 12, 6, 14, this member 12 and 14 is not covered by any other group. But if you look at this group 4, 5, 7, 6, all of its members is already covered by another group. Like this 4 is covered by this group, and 5, 7 is covered by this group, and so on and so forth. So that's a non-essential prime implicant. So we can drop directly any non-essential prime implicant from our reduction step, okay, or reduced expression. Even if we write them, let's say you're writing this non-essential prime implicant, which is essentially your w bar x, right? W bar x. We can, from here we can reduce to there by consensus theorem, right? So look at this, like I have two variable, which is like two term w bar and x going with z and z bar respectively. Then we are combining this w bar and x, right? So that's by consensus theorem we can drop this term, and I hope you all remember how this can be proved, or these steps can be done with using the Boolean identity functions. All right. But okay, we can apply the consensus theorem here directly, and we can just drop this term from there. So point is that even if you write down the non-essential prime implicant in the reduced form, in the reduced expression, it can be further reduced and eliminated from that expression, right? So if you include non-essential prime implicate, you are essentially not writing the most reduced form that can be derived for this SOP. Now, there can be a situation where selecting one essential prime implicant will make another prime implicant non-essential. Okay, so let's take this example, and we covered everything else with the groups, maximal group. Now we are trying to cover 15. We have two possibilities at this point. We can group 13, 15, or we can group 15, 11. All right. So which one to take? Now see, if I take the red one, 13, 15, then it will make 15, 11 as a non-essential group. Or we can take the blue group, 15 to 11, which will make 13 and 15 non-essential. All right. So at this point, let me tell you one thing. Like in this class, we'll follow this thing. Like in internet and maybe in the other math discussion, what by definition they want to give that, hey, your group 13, 15 or 15, 11 is not an essential groups. Your essential groups are all other groups because they are covering distinctly in one. But in this class, and what I define, I like to define is that you have to make one of them essential. You have to make either this 13, 15 an essential, because you need to put it in your expression. You cannot avoid them, right? So you are kind of choosing between two groups and marking them as it is an essential for me. And that's the definition of essential prime implicant in this class, which differs from any other mathematical Boolean algebraic discussion you will find in the book or in the internet. But this is in this class, okay, because I think this is the right thing to do. We need to include one of this term to complete our expression, and that makes it essential. All right. So we make or declare one of them as an essential prime implicant. Now selection rules states that select non-overlapping essential prime implicant as much as possible. We'll see why with this example. So we have an example of SOP, which is summation of minterm 0, 1, 2, 4, 5, 10, 11, 13, 15. We start grouping them. And there is one possibility of group like this, right? So we are selecting all the essential prime implicant like this group. There is another possibilities which can be like this, right? This is also some similar thing, right? We can group. They are all essential prime implicant if we think of in that term. But not this is also an possible grouping, right? They are all essential prime implicants. So we have like couple of choices here to select essential prime implicant. Okay, couple of combination of choices. Now we don't want to pick up a choice which gives me more overlap with each other. That's what the selection rule is saying. See, in this last combination, we have like 1, 2, and 3 overlap between the essential prime implicants, whereas the previous one has 1 overlap, another one has 1 overlap, so we are okay with them. But the last one will definitely give us more term, which is not an essentially an most reduced form. Okay. So that one thing you need to understand and apply selection rule whenever it is applicable. And don't care term. Now, this is more closely related to the digital logic design problem. Okay, just don't ask me right now where these don't care terms come, etc., etc. We'll see it in later example in other lectures. But point is that in digital logic design problem and Boolean reduction problem, often there comes a time when there is a don't care term. And what do I mean by don't care term? It usually appear like this. Okay, my SOP is, let's say, is a sum of 1, 3, 7, 11, 15, and D as in don't care is 0 to 5. 0 to 5. Okay, 0, 2, and 5. So what does it mean? So remember, this is the mean term we are talking of, mean term 0, mean term 2, mean term 5. What essentially the problem, original problem statement from where the truth table was derived is saying that in my lifetime of operation of this digital circuit, I don't expect a value combination of W, X, Y, Z, these variables, which leads to mean term 0 or 2 or 5. They don't appear in the lifetime. Okay, so that becomes a don't care term in our problem. Okay, and let's see how we can make it as an advantage for reduction steps. So for don't care term, along with the ones, we put a cross in those corresponding boxes 0, 2, and 5. And then we, for example, we can group them like this, like without considering the don't care. If we didn't take advantage of don't care, what we can do, we can group 1 and 3, and then we can make a group of 4 of 3, 7, 15, 11, and my reduced form would be this. Now the don't care term usage is saying that use a don't care term or treat a don't care term as logical 1 if and only if it helps you to make a bigger group. Okay, if and only if it needs to make you make you a bigger group. This means essentially you don't need to include all the X all the time. Don't treat them as 1. You treat them as 1 only if it helps you to make a big groups. Okay, only if it helps you. So essentially that another thing it means, you should not or you cannot make a group which contains only X's. That doesn't make sense, because a group of X won't appear in your logic operation in the lifetime of the logic circuit. So you should not group all X's together. That means like a group contains all X's is not needed. You should not do it. And secondly, you should treat X as 1 only if it helps you to make a big group. So in this example, in this context, we can have a bigger group from 1, 3. Instead of that, we can do this 0, 1, 3, 2, or we can do this X as 1, 3, 5, 7. Okay, so both of these answer is correct. Okay, so you can reduce instead of W bar X bar Z, we can come up with an W bar X bar or W bar Z, treating on which one I am including or treating as 1. Like for blue group, I was treating X like 5 that box as 1. In the red group, I was treating 0 and 2 as 1. My personal preference is try to use X as less as possible. Okay, so I would prefer to have an answer and reduced form of these because this guy involves less number of X than this red one. But point is that please use it if it helps you form a bigger group. You should not reduce to this because you have a don't care. Okay, so that's the essential need things to understand. Okay, so if there are X, try to use it. Okay, and try to use it in minimum. All right, that's the key point of it. That's all for this lecture, lecture 5, and next lecture we'll start reviewing the digital logic design aspect of our study.